Hello, I'm Doug Waples. Today I'll be presenting a video that shows much of the basic workflow in creating a good geologic model for a single well. We'll start with a rough model that was based on several concepts and assumptions about the tectonic, depositional, and thermal history at the model location, which sits in a complex area that appears to have experienced at least one major erosional unconformity. We'll examine the model in detail, beginning with the geologic data and, very importantly, a clear acknowledgement of the gaps in our data and uncertainty about the assumptions involved in building our original model. I'll then propose some significant modifications to those assumptions that will lead to significant revisions of the ideas in the original model. The purpose of this video is to show both the thought process in building good models and the importance of using the best possible assumptions, data, and data interpretations in building the models. Our model for this video is the Münsterland 1 well, drilled to a depth of about 6,000 meters in 1961 for scientific purposes by the West German government. Data from the well were subsequently studied thoroughly by a large team of German scientists. The Münsterland 1, or M1 well, is shown in the lower map here as a red dot in the middle of the Münsterland basin, which sits to the north of the current exposure of the Rhenish Massif. That massif consists of many thrust slices emplaced during the Variscan orogeny in the late Carboniferous. The upper map places our small study area in the context of Northwest Europe. The location is very close to the Dutch-German border, not far south of the North Sea. The Münsterland Basin, also known as the Münsterland Cretaceous Basin, or the MCB, is just south of the larger and better-known Lower Saxony Basin and somewhat north of the well-studied Tertiary Age Rheingraben. As we will see later, however, there are a number of major and critical differences between the Münsterland region and the nearby basins. The Münsterland 1 well was in fact the first well for which a burial history curve was ever published by Nikolai Lopatin in his landmark 1971 paper that introduced his TTI method, the precursor to modern basin modeling. M1 was, not coincidentally, also the first model I ever created, so there's a good bit of nostalgia for me as I revisit it. Today we'll be analyzing the well's history in detail, in a way that was not only impossible to do in the 1970s, but impossible to even imagine doing. We've truly come a long way in the past 5 decades. All models are created using a mixture of facts and assumptions, and we must be vigilant about keeping what we know separate from what we think may be true. The geohistory plot presented on this slide is no exception. It was created quickly using a variety of data and ideas, and possibly even a few concepts, but it is not a finished and proven reconstruction. Our specific objectives today are to break down the components of this Münsterland 1 model and examine them, to improve our understanding of the integrated geologic history at the model location, and finally to build a better model. Our broader objective in this video, of course, is to learn how to do this type of critical thinking and analysis routinely. The shape and details of the M1 geohistory plot quickly indicate several important details that we, with a bit of knowledge of local and regional geology and plate tectonics, can relate to specific geologic events. For example, on this slide we see a period from about 335 MA to 300 MA of very rapid sediment accumulation. A portion of this part of the model is essentially fact, supported by the well-known ages and thicknesses of the Carboniferous rocks present in the well. But the geohistory plot also includes a hypothesis, shown in the annotation, that the rapid Carboniferous deposition corresponds to development of a foreland basin in front of the Variscan orogeny. Once those two sets of information are juxtaposed in one's mind, it is easy to make the mistake of believing they are inseparable and that both are entirely factual rather than partly interpretive. Here I have added a second interpretive comment, Variscan orogeny, derived from the well-documented existence of a major unconformity that is believed to have begun near the end of the Carboniferous. The precise age at which subsidence changed to uplift at this location is unknown, but I have assigned it here an age of 300 million years, which is surely not far from the truth. The change from deposition to erosion is a fact, but the timing is an assumption that has some range of uncertainty. Fortunately, probably no more than a few million years. We also interpret with our comment that the uplift means the Variscan orogeny, sensu stricto, had arrived at our modeled location, and that the foreland basin stage was now over. Logical and obvious as this comment seems, it is still an interpretation rather than a fact. That uplift and erosion occurred is a fact. That they are related to the Variscan orogeny is an interpretation. This model also shows our interpretation of the elevation of the Variscan mountains as a function of time. The elevation history shown here is not based on data, but rather develops from our interpretation of the magnitude and timing of uplift, and of timing and amounts of erosion, both synorogenic and post-orogenic. We'll discuss those points later in more detail. Please note that the ages and thicknesses of the eroded rocks are not data, since they are inferred rather than directly measured. As we will see later, those inferences can be tested using measured thermal indicator data during the model optimization process. A vital part of this initial model is the reconstruction of the period from the late Permian through the Middle Jurassic, where our model proposes accumulation of a thick marine section that has subsequently been completely eroded and thus isn't present today. The thickness of the postulated section was not extreme. It doesn't present a problem in terms of the sedimentation rates required. The concern lies elsewhere. The model as proposed requires bringing the top of the Variscan mountains down below sea level in quite a short time. What mechanism or driving force would justify this proposed subsidence? The concept of rapid subsidence is not unusual or particularly difficult, but juxtaposing it with a thrusting event does create mechanistic issues that must be addressed. In addition to the complex mechanics involved, we must also ask why we would even be tempted to deposit and erode the Permo-Jurassic section. Why not simply assume continuing erosion of the Variscan mountains, permitting them a gradual and graceful, rather than abrupt, subsidence into the sea? Is the Permo-Jurassic sedimentation event pure fantasy, or does it have its foundation in real data from nearby areas? And if such data exist, how trustworthy, relevant, and convincing are they? For the moment, we have no answer, but we shall return to this key issue in the very near future. Deposition of Permo-Jurassic strata in our model creates another problem. Since those layers aren't present today, they must have been eroded. In this case, knowing the timing of erosion isn't much of a problem, since a thick sedimentary section spanning 2/3 of the Cretaceous sits atop the eroded Carboniferous. We therefore know that erosion of the proposed Permo-Jurassic started no earlier than late Jurassic and ended no later than Albian, if it was deposited at all. But we also need a mechanism for this erosion. In the current model, after 100 million years of subsidence, we must uplift and erode those same sediments during the next 50 million years. What would be the driving force for this significant late Jurassic uplift? and how much topographic relief would it have created? And deposition of the Cretaceous in our model creates still another problem. We know Cretaceous strata are present today, and we think we have a good idea of their original thickness. But we don't yet know how the required accommodation space was created so rapidly after erosion of the Permo-Jurassic section. We also don't know yet where the Cretaceous sediments would have come from. Are they derived from the remains of the aging Variscan mountains? Or do we have a new source terrain, perhaps one with different possibilities to produce reservoir facies or seals? Or, since much of the Cretaceous section is calcareous, perhaps the sediment source is simply the marine organisms themselves. It's all food for thought as we develop our conceptual model. Perhaps it's time to rigorously compile everything we know or think we know from our data, concepts, ideas, and interpretations. In order to deal with all the issues that will arise, it's useful to make two lists. One is a list of things that we know or think we know. The other will be a list of things that we don't know. Here I've begun by compiling a list of the data and facts we have at our disposal and that we must honor. We could make an even longer list, but our time is limited, so I will stop here for the moment. In dealing with the issues we have just mentioned, we will undoubtedly discover other questions that need answering. That's part of the excitement and value of this journey. Let's start with the easiest items, which most people would think are either trivial or irrelevant. But present-day location and elevation are both important. The present-day location will enable us to track our model's latitude and position with respect to other tectonic plates through time, while the present-day elevation will have to connect to the Paleo elevation history that we eventually reconstruct. The red dot on this map marks the Münsterland 1 location, very close to the Dutch border in northwest Germany. That its elevation is only 25 meters today is no surprise. In this figure, we also see its location with respect to thrusts on the Rhenish Massif, in what used to be the Variscan Mountains. The well is just at the northern edge of the thrusts, which advanced from the southeast. This information will be important in understanding the Paleo elevation story during and following the Variscan orogeny. By the way, the names Variscan and Hercynian are largely interchangeable, although Variscan, which I am using in this video, seems to be slightly preferable in this area. We also know the present-day stratigraphy in Münsterland 1 quite well. In fact, the model's stratigraphy, shown here, is a rather simplified representation of the known stratigraphy. However, it will work quite well for our purposes. What the present-day stratigraphy lacks is obvious. Information about strata that have been removed by erosion. A definite statement on whether missing time intervals actually included depositional events, and if so, what were the details of those events. We've already seen one complete reconstructed geohistory plot showing our starting version of the geologic history at Münsterland 1. However, as we have already discussed, that geohistory included a large amount of interpretation. Now I want to show a different type of geological history plot that contains very little interpretation and thus serves as a more neutral beginning for the model building process. This is a burial history plot in which water depth and elevation, which are included as crucial components of geohistory plots, are omitted. In fact, this special version is even simpler and less accurate than a normal burial history plot because it has made no effort to reconstruct events at the unconformities. It has simply considered each unconformity to be a hiatus. To repeat, it is not a realistic model, but it is a useful, unbiased starting point based only on data. The red arrows at the right designate the two unconformities that are definitely present in our model. The earlier one is between the Carboniferous and the Cretaceous, and the later one is at the surface above the Cretaceous. Please note that the plot doesn't show the Permo-Jurassic section or its deposition or erosion, since there is no conclusive evidence from the present stratigraphy alone that it was ever present or what it might have consisted of. Similarly, there is no information about possibly eroded rocks above the preserved Cretaceous. This approach more than makes up for its deficiencies by allowing us to reconstruct the details of those unconformities with fresh eyes. By the way, I consider the concept of fresh eyes to be crucial to successful modeling of geological histories, so don't be reluctant to discuss your models, even unfinished or difficult ones, with your colleagues and with other geoscientists who might not even be directly interested in basin modeling. Everyone sees some things that others would miss. Downhole temperature data are of great value in modeling of thermal histories. Fortunately, in the Münsterland 1 well, we have a nice set of downhole temperatures obtained from numerous wireline logging runs. This plot shows the temperature data that I was originally given for the Münsterland 1 well. The temperature profile is excellent and certainly seems at first glance to give a clear answer about the present-day thermal regime. Unfortunately, I was not told whether or not the temperatures had been corrected, and if they had been, what method had been used. I was concerned because the data were published in 1963, long before modern methods for correcting wireline log temperatures had been published, and I was concerned that the trend of temperature data was too perfect to be believable. Anyone who has worked with real downhole temperature data would likely be just as suspicious as I was of a trend as nice as this one. This is the information I had to start with about present-day temperatures. I'll tell you the rest of the story a bit later. It does have a very happy ending, but probably not the one you are anticipating. Thermal indicator data are also of great value in modeling, especially where there are major unconformities and major uncertainties about those unconformities, or where paleo heat flow might have been different from present-day heat flow. Fortunately, in the Münsterland 1 well, we have an incomparable set of vitrinite reflectance values measured on a large number of carboniferous coal samples by world-renowned experts. The reflectance data range from moderate maturity levels to extremely high ones. Unfortunately, low maturity data are absent in the Paleozoic samples analyzed. Apparently, no reflectance data were obtained from the Cretaceous. The lack of reflectance data from the Mesozoic is understandable in an historical context. In 1962, reflectance had only ever been applied to coals. It had never been used for kerogens or rocks that didn't contain coaly material. The Carboniferous in Münsterland 1 was very rich in coals, but the Cretaceous was not. This is one of those rare and extremely happy occasions where the RO data appear to be completely trustworthy. The increasing scatter in data at the bottom of the section, where maturity is extremely high, is unavoidable since it stems from increasing anisotropy of the vitrinite particles. Moving on with our list, we know today with reasonable accuracy the plate tectonic setting and history of nearly any location on the planet. This reconstruction shows the Münsterland 1 location, the red dot, in the late Carboniferous at 302 MA, just before uplift created the Variscan unconformity. The well sits in the middle of Pangaea, at the complex intersection of several agglomerated continents and microcontinents. The green dot shows the Münsterland 1 location in a more zoomed-in view at about the same time. The Avalonia, Baltica, and Laurentia, that is North American, plate names are circled in red. Note the well's position on the leading edge of one of the Variscan thrusts on the Rhenish Massif that move from the southeast. Those thrust edges are shown by the dotted lines to the east and south of the green dot. The plate tectonics history helps us understand the nature of the complex collision during the late Paleozoic that resulted in the Variscan orogeny. This knowledge is crucial for creating a realistic model for the orogeny and for the post-orogenic history. The small red dot shows the approximate location of the Münsterland 1 well 400 MA as various continents and microcontinents approached each other, well before the start of the Variscan orogeny. Another reconstruction from about the same time confirms the same basic pattern of the preliminary stages in the assembly of the northwestern part of Pangaea. Our well is again indicated by the red dot. Slightly later, the major docking of Laurussia with Gondwana is well underway. The Münsterland 1 location, the red dot, is not involved in a major collision. Finally, by the late Carboniferous, the Münsterland 1 location is surrounded by the gathered continental fragments. And so, as Wikipedia says, the Variscan orogeny involved a complicated, heterogeneous assembly of different microplates and heterochronous collisions. The Alleghenian orogeny is the North American name for what is called the Hercynian orogeny in Africa and in parts of Europe. It is shown here as the western portion of the Yellow Mountains, which have an east-west orientation. The small six-pointed red star sits approximately at the eastern end of that orogeny. Some people might take the Alleghenian orogeny as a good model for what happened at Münsterland 1. However, the Alleghenian orogeny involved a strong and direct collision between two massive plates, Laurentia and the African portion of Gondwana, whereas the collision further east that directly affected Münsterland 1, shown by the red dot, was much less direct. The collision at M1 might be compared to a group of bumper cars coming together in an amusement park, rather than as a head-on collision on the freeway. When we think of continental collisions and suturing, the most obvious example to many of us is India colliding with Eurasia. This topographic representation shows the net result of that collision, a thin line of extremely high peaks, the Himalayan ranges, that separates the uplifted Tibetan Plateau, with an average elevation of about 4,500 meters, from low-lying India. India striking Eurasia seems to have been rather like a spear into the heart. Even during the approach of the two continents, the potential for major pain and suffering was evident. From the Eocene to the present day, India has pushed itself deeply into the side of Eurasia. This striking representation shows clearly the asymmetry in the results of the collision, as India was subducted beneath Eurasia. The map also shows that the vast majority of the area affected by the collision is not at extreme elevations. We therefore shouldn't think that every continental suture produced mountains 5 to 10 kilometers high, nor that such mountains, where they did form, represented a large portion of the landscape. But beyond those caveats about misusing the most extreme features of a compressional setting as typical characteristics, there are other reasons to believe that India-Eurasia may be a poor analog for Münsterland. This slide shows interpretive cross-sections through time, with the oldest on the bottom, across the Alleghenian orogeny, which sutured Morocco to the southeastern U.S. India clearly lost the battle with Eurasia and was subducted, but the Alleghenian orogeny produced more of a draw than a winner and a loser. Continental thickening and uplift occurred on both sides of the vanished ocean. The Variscan orogeny, which is considerably to the east of the Allegheny orogeny, was probably much weaker because of the aforementioned bumper car effect. Subduction or extreme compression seems unlikely. The red dot on the map on the left shows the location of the M1 well in the Alleghenian Variscan system. Further to the southeast, on the older parts of the Rhenish Massif, the 2005 fish and track data of Karg and co-workers indicate larger amounts of erosion, and thus probably more thrusting and higher mountains. We've talked thus far about what we do know and how well we know it, but it's necessary to also discuss the things that we don't know about Münsterland 1. Most of those knowledge gaps are related to the tectonic history. These gaps often combine to give us potentially large uncertainties about the thermal history in terms of depth of burial at different times, paleo surface temperatures, and heat flow out of basement through time. The blue items at the bottom of this slide relate to uncertainties about the model's calculations of hydrocarbon generation. Although they are real concerns, today we'll focus on issues related to the geological and thermal history, and we won't be discussing source rocks, kinetics, or hydrocarbon generation. The items in red at the top of this list are directly related to the unconformities. They involve reconstruction of events during each unconformity and the implications of events during the major Variscan unconformity for paleo temperatures. Here's our original geohistory model again, just to refresh your memory. And here is that original geohistory plot with red arrows indicating a variety of events that we have consciously or unintentionally defined in the process of building this rough draft model. We'll go through all of them, from the oldest on the left to youngest on the right, so that we understand the implications of our data and assumptions in creating this model. The green arrow here shows that Variscan effects began to be felt no later than 335 MA, with an increase in sedimentation rate. One could also argue that the effects actually began earlier, at about 365 MA, with the increase in water depth as sediment supply initially failed to keep up with a tectonically induced increase in subsidence rate. The green arrow at the bottom of the slide at 300 MA shows the moment of maximum burial, just as the Foreland Basin began to invert, as the Variscan thrusting moved into the Münsterland 1 location. The timing of this inversion is dictated by the age of the youngest Carboniferous sediment we have allowed to be deposited. As noted earlier, there is an uncertainty of perhaps a few million years in this exact date. The horizontal green arrow at the top shows that we have proposed a maximum elevation of 3,000 meters above sea level at 280 million years. We should be able to provide good justifications for both the elevation and the dating, and if we can't, we should investigate further. The blue arrow shows that in our model, erosion began at the onset of uplift and continued until the start of Permian sedimentation at 256 MA. It can't be seen easily on this scale and in this type of diagram, but the rate of erosion decreased substantially from relatively high rates between 300 MA and 290 MA to lower rates after 290 MA. Be prepared to defend the rate or rates of erosion at different times during the unconformity, taking into consideration type of sediment, climate, erosion mechanisms, and topographic relief. The green arrow here points out the initiation of the late Permian through Middle Jurassic depositional phase that we have proposed, even though there is no direct evidence for it at the Münsterland 1 location. The blue arrow represents the long period allocated for deposition of those Permo-Jurassic sediments and the downwarping that enabled that deposition. Be prepared to discuss thickness, the beginning and end age for each depositional event, and lithologies deposited, as well as comparable details for all phases of erosion. The green arrow on this slide shows the uplift and erosion of the entire Permo-Jurassic sequence. Be prepared to discuss the uplift and erosion mechanisms and details, such as timing and rates. The blue arrow indicates deposition of the Cretaceous section, which is not in doubt. However, the arrow serves to remind us of the need to understand both the cause of the creation of accommodation space and the source of the Cretaceous sediments. The horizontal green arrow again serves to remind us of the need to distinguish the tectonically active Cretaceous from the very quiet Cenozoic, and to understand the mechanism that terminated Cretaceous subsidence and sedimentation. This slide provides a rewritten summary of most of the work points made on the previous geohistory plots. It's mainly here for future reference. Many tectonic events are associated with thermal anomalies, so it's always a good idea to investigate that possibility. Of particular interest here is the Variscan event, because it appears to be the strongest tectonic event in the well's history, and because it is associated with proposed maximum burial and temperature. But we're going to defer discussion of all thermal issues until we finish with the tectonic events. As we just saw, it's important in building a good geologic model to understand cause and effect relationships. Many such relationships begin with tectonics. I therefore think it's very useful to attempt to recreate and understand the tectonic events in the model's history. We have already seen this philosophy in action to some degree, but now we're going to take a slightly different approach. I've begun by very quickly assigning several tectonic events to the geohistory as overlays. The earliest of the events are development of the Foreland Basin, followed by the Variscan uplift itself. Then, to explain the collapse of the Variscan Mountains and the deposition of a moderately thick late Permian, Middle Jurassic section, I've proposed a long sagging event, probably relaxation devolving from the disintegration of Pangaea. The fourth event is largely a guess. We need some mechanism to terminate Jurassic deposition and provide a platform for erosion of the entire lower Mesozoic section. Here I've just called it unknown uplift. I hope to be able to clarify its origin later in the analysis. Finally, the fifth event, which enabled deposition of the Cretaceous section, suggests some kind of rapid extension, as either a pull-apart or a rift. Again, I hope to shed more light on the details as the analysis proceeds. These 5 events will help us get started. It is very likely that our list of events will change significantly as we learn about the Münsterland 1's history. There are obvious improvements that could be made in our estimates of the timing of the various events. The start of the Variscan Foreland episode, shown by the red arrow, could easily be pushed back from 318 MA to 365 MA, as it initially developed as a starved basin with increasing water depth, before a flood of sediments from the Variscan origin filled it. The end of the Variscan uplift, indicated by the blue arrow, might be better placed at peak elevation, 280 MA, than at 271 MA. That new date might also be a better time to initiate the disintegration of Pangaea. We might push the end of the disintegration phase back to 160 MA to correspond better with the end of Jurassic sedimentation. We could initiate the period of unknown uplift at the same time, as shown by the green arrow. The end of the uplift probably occurs earlier than this diagram says, and doesn't necessarily coincide with the onset of the early Cretaceous extension. The proposed extensional event in the Cretaceous, shown by the orange arrow, appears to have begun with the renewal of sediment accumulation in the Aptian, and ended at 82 MA, when the most rapid phase of subsidence ended. The rift phase seems to have been followed briefly by a drift phase from 82 MA to 67 MA before it was terminated by another uplift event. The same geohistory plot with the revised events superimposed is shown here. It doesn't provide a complete or quantitative analysis of the tectonic history, but it does give us a better guide in going forward with the analysis. Analysis of tectonic uplift and subsidence provides another invaluable tool for understanding the integrated geological history. This slide shows the same geohistory with the tectonic events removed for clarity, and with a red tectonic subsidence curve now superimposed. Upward movement of the red line indicates that tectonic forces are moving the rocks upward with respect to the datum, which in this case, and in most cases in this presentation, is Paleo sea level, while downward movement indicates tectonic subsidence. Our other geohistory plots all use Paleo sea level as the datum, so the surface of the ocean was at a constant elevation of 0 through time. However, when one wants to emphasize the role of eustatic sea level, it may be more useful to take present-day sea level as the datum. In such cases, as shown here, the surface of the ocean goes up and down through time. These plots are actually more realistic than the ones with flat sea level, but as they are new, they are unfamiliar and even disconcerting to some people. In this presentation, I'll use a mixture of the two styles, depending on what I am trying to say. The development of the Variscan-Foreland Basin involves considerable tectonic subsidence, as shown by the blue arrow, and the Variscan orogeny in orange requires tectonic uplift. But what is most interesting here is the massive tectonic subsidence required to bring the high proposed Variscan mountains back down below sea level in order to initiate deposition of the Upper Permian marine Zechstein evaporites. This tectonic subsidence, shown by the red arrow, parallels the decrease in surface elevation. Erosion alone is not adequate to bring the Variscan mountains to sea level, since isostatic forces keep pushing the land surface back up nearly as fast as it erodes. Isostatic responses, even imperfect ones, are important to the story here, and in many other places. This result from combining these various technologies and phenomena, eustasy, isostasy, tectonic uplift and subsidence curves, and geohistory plots, shows us very clearly that our proposed model is probably not realistic. In particular, I think we need to reduce the required amount of tectonic subsidence of the Variscan mountains. The next slide shows one possible improvement in the model. If we reduce the paleo elevation of the Variscan mountains, it of course becomes easier to eventually bring them down to sea level. In this slide, we have reduced the maximum paleo elevation by half, from 3,000 meters to 1,500 meters, with a proportional decrease in the amount of required tectonic subsidence. It is very important to understand that this change only affects paleo elevation. The amount of erosion wasn't changed. We're simply saying that more of the erosion was syn-orogenic. If the amount of required tectonic subsidence is still more than we can accept, we can further reduce the paleo elevation, as shown on the next slide. Here I've reduced the maximum paleo elevation to only 500 meters, and our Variscan mountains have become the Variscan hills. Our model still requires some tectonic subsidence, but that amount may be acceptable for some tectonic models. At this point, we haven't proven that this solution is geologically acceptable. For me, it is much more attractive than the original high mountain scenario, especially given the lack of evidence that high mountains actually existed. But it is not the only possible model for the Permo-Jurassic history at Münsterland 1. So let's switch gears and focus a bit on late Permian through Jurassic sedimentation in northern Germany. This block diagram shows the Permo-Jurassic section in northwest Germany, represented by the purple, pink, and blue colors, as indicated by the vertical red lines on both the legend and the diagram. These are the strata that were deposited and subsequently eroded in our original model. Those layers are clearly present over the northern part of the area, which is to the left in this slide, but it's also obvious they are missing in the south on the right side. The same area is shown here from a different perspective that includes the Münsterland 1 well, which is indicated by the red dot on the green Cretaceous surface. Triassic and Jurassic strata are absent in the well, but are present not far away. Is their absence in the well due to erosion, as our initial model proposes, or perhaps instead to non-deposition? We'll now examine the paleogeography at and near the Münsterland 1 well in the context of events from the late Permian until the late Jurassic, beginning here with Upper Rotliegend 2, deposited during the late Permian. This map shows the M1 location, indicated approximately by the red star, as emergent at that time, with Rotliegend deposition limited to the area further to the north. In fact, the southern limit of Rotliegend deposition may well have been, wholly or in part, defined by uplifts created during the Variscan thrusting. During Muschelkalk time, from 247 MA to 237 MA in the Middle Triassic, the M1 location was right at the margin of the Rhenish Massif. If it was on the emergent Massif, as I believe it was, significant accumulation would have been very unlikely. We see the same pattern here during the early Jurassic, with the Rhenish Massif emergent and the M1 location right at the northwest margin of the Massif. Another source, Rickard and Wilmsen in their 2012 publication, said that, quote, through Permian to late early Cretaceous time, the Rhenish Massif was an area of non-deposition and erosion, including both the Ruhrgebiet and the Münsterland, unquote. They and other workers have noted the large difference in Mesozoic history between the Münsterland area and the Lower Saxony Basin just to the north, where the Upper Permian, Triassic, and Jurassic are all well developed, as we have seen in the preceding slides. The appetite fission track data of Karg and co-workers from 2005 indicate a possible heating and subsequent cooling event in the Mesozoic that could be explained by sedimentation followed by erosion. However, their closest data to the M1 well do not show this effect, and the Mesozoic history of the Ruhr Basin, where most of their samples were from, may well have included at least some Permo-Jurassic marine sedimentation that I personally doubt occurred at M1. The areas that were flooded by marine incursions during the late Permian through Jurassic were mainly the lowlands that formed as a result of extension as Pangaea disintegrated. Those areas lay to the north of the Münsterland 1 well. There may also have been some sediment accumulation in some of the valleys between thrust sheets. In contrast, the thrusted area of the Rhenish Massif itself, where we are confident the M1 well was located because of the erosion it experienced, remained high and dry. In support of that idea, this cross-section shows the Münsterland Cretaceous Basin, or MCB, where the Münsterland 1 well is located, as shown schematically by the green arrow. The red ovals show Upper Permian through Middle Jurassic strata present in the northern part of the MCB, but pinching out depositionally toward the south. Succinctly stated, it seems that if we want to propose large amounts of erosion at the top of the Paleozoic section in the M1 well, the well must have been situated atop a thrust, a topographic position that would have prohibited it from accumulating sediments during the Permo-Jurassic. This change in our thinking offers us an easy solution to the problem of overly rapid subsidence of the mountains, because the development of marine conditions can be postponed nearly 150 million years until the Aptian. So now let's look at some scenarios in which we don't have to deposit and erode sediments of late Permian to Jurassic age. This geohistory plot returns to our original hypothesis of 3,000 meters maximum elevation at 280 MA. The downward trend in surface elevation from 280 MA to the restart of deposition in the Aptian is intentionally more or less exponential, reflecting a common and reasonable concept that erosion rates tend to decrease with decreasing topographic relief. We note that one consequence of the 3,000 meter maximum elevation is that there must have been a major component of tectonic subsidence during the Permo-Jurassic, as shown by the downward trajectory of the red tectonic subsidence curve. Erosion alone is not enough to bring the land surface down to sea level because of the rebound effects of isostasy during unloading. If we reduce the maximum elevation to 500 meters, we note that a minor amount of tectonic subsidence is still required during the main erosional episode in the late Permian. If we reduce the maximum paleo elevation further to 400 meters, the need for tectonic subsidence disappears completely, as the red tectonic subsidence line remains flat until the beginning of Cretaceous subsidence. This is my preferred model for the Variscan, although there isn't any reason that there couldn't have been some tectonic subsidence during the disintegration of Pangaea in the early Mesozoic. We do note, however, that the fragmentation of Pangaea did not produce any major tectonic events at the M1 location, in spite of evidence for major effects a bit further north. Having reached at least a tentative decision about the early Mesozoic, we can turn our attention to the Cretaceous, which is definitely present in the Münsterland 1 well. As we saw earlier, the Cretaceous in the M1 well was deposited as the main step in the development of the Münsterland Cretaceous Basin in the Albion. The MCB sits between the thrusts that separate it from the North German and the Lower Saxony basins to the northwest and northeast, respectively, and the thrusts of the Rhenish Massiv to the south. In fact, the northern margin of the Rhenish Massiv, including the M1 location, sank during the Cretaceous, allowing the MCB sediments to onlap onto its northern margin, as shown here by the blue arrow. This block diagram may show the Cretaceous onlap onto the northern margin of the Rhenish Massiv a little more clearly. The major global sea level high stand that occurred at 53 MA was nearly 240 meters above present sea level. We will see that high sea level stands and variations in sea level were important in the Cretaceous and Cenozoic history of the study area. The nearly 2,000 meters of preserved Cretaceous section in the M1 well represents a major event with important implications for our entire reconstruction and deserves commensurate attention. Here we see the standard geohistory plot for the well using relatively modest elevations during and after the Variscan orogeny. Because global sea level was changing greatly during the Cretaceous and Cenozoic, it is useful now to look at the new type of geohistory curve, shown here, where the datum is present-day sea level and the sea surface thus goes up and down through time. If we toggle back and forth several times between the two diagrams, you can get a feeling for the differences in the two presentation modes. In 2012, Rickart and Wilmsen stated, quote, The global Albian-Turonian sea level rise, 40 meters as shown by the red arrows marking the beginning and end, caused a major onlap of nearshore and hemipelagic strata onto the northern part of the Rhenish Massif, transferring the Münsterland into an area of deposition. This was the birth of the Münsterland Cretaceous Basin, which was part of the wide North German epicontinental shelf. A major period of this transgressive phase occurred during the Cenomanian, when the coastline shifted far southwards. Inversion of the Lower Saxony Basin began in the early Coniacian, locally already in the late Turonian. The inversion converted the former Lower Saxony Basin into the present tectonically stable Lower Saxony tectogene, while simultaneously the Münsterland Cretaceous Basin experienced significant subsidence, up to 2,000 meters thick sediments of Coniacian, Lower Campanian Emscher Formation, unquote. But the whole story may be even more complex, and analyzing the geohistory plot provides additional insight. We note here that there is considerable tectonic subsidence associated with the Cretaceous deposition. The early subsidence phase, depicted by the dark red arrow, was gentler than the second phase, shown by the bright red arrow. Therefore, use to see alone was inadequate to account for the 1,800 plus meters of Cretaceous sediment. We observed the same phenomenon in our study of the Permian Basin in West Texas in the U.S., where rising global sea levels had generally been considered to be the cause of formation of the Cretaceous Western Interior Seaway that bisected North America. We suggest that both tectonic subsidence and Eustace played roles there as well as here. Mid to late Cretaceous tectonic subsidence in the MCB was concurrent with inversion of the Lower Saxony Basin to the north and east. This juxtaposition, together with the speed and intensity of the second subsidence phase, suggests some kind of transtension. Now let's shift gears away from the tectonic events and look in detail at the thermal aspects of the model, starting with present-day downhole temperatures in the M1 well, which are shown in this profile. In analyzing temperatures, it is normal to begin with the present day because we can directly measure present-day subsurface temperatures and because those temperatures will give us clues about paleo temperatures. The temperatures in this plot, which we saw on an earlier plot, are the ones I was originally given without attribution. They turned out to be estimates of true formation temperatures based on wireline log temperatures. This work was published in 1963, which long predates the development of the standard methods for correcting wireline log temperatures that we use today, and as such they needed to be reviewed carefully and possibly revised. The basal heat flow required to achieve this fit to the two deepest supposedly true formation temperatures is 54 milliwatts per square meter, as shown in this profile. If we had chosen to fit any of the other data points instead, the required heat flow would have been somewhat lower, as shown in this profile. The required basal heat flow to achieve the fit to the next two deepest supposedly true formation temperatures is 52 milliwatts. It took some research to find the original wireline log temperature data, but here they are, the uncorrected measured temperatures. There's a lot of data, and most of it is quite consistent. Here we see the uncorrected wireline temperatures as open green circles, and the estimated true formation temperatures as red open triangles. Heidemann did not describe his method for correcting the log temperatures, but his correction is very small and is least at the greatest depths, where temperatures are highest. The inclusion of the uncorrected temperatures doesn't change our fit to Heidemann's corrected temperatures, but the very small amount of correction used by Heidemann suggests to me that he has probably underestimated the true formation temperatures. Modern methods of correcting wireline log temperatures generally give larger corrections than Heidemann used. My preferred correction method is based on large studies we carried out in the Malay Basin, the Gulf of Campeche in Mexico, and the Danish Central Graben of the North Sea. Here and in our NOVA software, it is called the MYMX-DK method. This plot shows the uncorrected log temperatures and Heidemann's corrected temperatures as before, plus the corrected temperatures using the MYMX-DK method as solid green dots with uncertainty bars. The gray calculated temperature profile was chosen to fit the new corrected temperatures and required a basal heat flow of 58 milliwatts per square meter instead of 54 milliwatts. This temperature correction method is mainly based on the time since the end of mud circulation. One might want to know about other correction methods. NOVA offers a method calibrated only on the Denmark data, and given the proximity of Münsterland to Denmark, it might be reasonable to inquire whether that method might be preferable, in this case, to the MYMX-DK method. This slide shows a plot of the uncorrected temperatures, Heidemann's corrected temperatures, and the temperatures obtained using the Denmark correction method. The deepest measured temperatures could not be corrected by this method, since their depths are beyond the calibration range for the Denmark method. But otherwise, the calculated profile and basal heat flow are identical to those used for the MYMX-DK method. The Denmark method is also mainly based on the time since the end of mud circulation. NOVA also offers the GSNA method, which was developed in the late 1960s by combining data from the Permian Basin of West Texas and the Gulf Coast. Many of the wells were deep, so corrections are available far below the base of the Münsterland 1 well. The amount of GSNA correction depends only on the depth at which the temperature was measured. Corrections are generally smaller than with the MYMX-DK method, and true temperatures are therefore lower. In this case, the profile is fit using a basal heat flow of 55 milliwatts per square meter compared to 58 milliwatts. A commonly used but not very scientific correction method is to simply add 10% to the measured temperature. Among its many disadvantages, one gets a different answer in Fahrenheit versus Celsius. Corrections are generally smaller than with the MYMX-DK method, and true temperatures are therefore lower. In this case, the profile is fit using a basal heat flow of 55 milliwatts per square meter, which is a bit lower than the 58 milliwatts required for the MYMX-DK method. So I think we can conclude that for the lithologies we are using in our models, the temperature data indicate a present-day basal heat flow close to 57 to 58 milliwatts per square meter. Overall, my confidence in our present-day temperature profile is extremely high. With the present-day thermal profile pretty securely in place, it's now time to think about paleo heat flow. Many tectonic events are associated with thermal anomalies, so it's always a good idea to investigate that possibility. Of particular interest here is the Variscan event, because it is the strongest one, and because its association with maximum burial and temperature will ensure its importance. But any analysis of the thermal effects of a tectonic event must view that event in a broad context, including events leading up to the main event and those events devolving from it. One way to begin the discussion of paleo heat flow is to simply try a constant basal heat flow through time and see what happens. And here is the result. Using a constant basal heat flow of 58 milliwatts per square meter through time, our calculated reflectance profile, shown by the two detached black line segments, does not completely fit the measured RO data, although the values at the top of the Carboniferous agree pretty well, and the calculated slope is only a bit too low. The gap or jump or dislocation in the calculated reflectance profile indicated by the red arrow, occurs because the Cretaceous rocks immediately above the Varisca nonconformity have had a much milder thermal history than the Carboniferous rocks immediately below them. The blame for a misfit between the measured dots and the calculated line can be laid either on the measured data, if their quality is questionable, or on the model, because models always have at least some uncertainty. Since in this case we trust the reflectance data, our model must be deficient. But what specifically is wrong with it? We've already noted that below the Varisca nonconformity, where the measured RO data begin, the slope of the black calculated reflectance profile is lower than the slope of the trend of measured reflectance data. Because both those slopes depend on the temperature gradient, real or proposed, at and near the time of maximum temperature, we could improve the fit by changing the heat flow we are using in our calculation of RO. Since the slope of the calculated trend is too low, we would have to increase the model's heat flow at the time of maximum burial, which we know from our geohistory plot must have been very close to 300 MA. Most people don't realize it, but there is a simple and legitimate way to justify a slightly higher heat flow in the past for any model. Radiogenic heat production from continental basement contributes a significant proportion of the total heat flowing out of basement. My own rough estimate is 50% of the total, plus or minus about 10%, with the proportion varying from place to place. So if we have a heat flow of 58 milliwatts per square meter at the top of basement, about 23 to 35 milliwatts comes from radiogenic sources. My best guess in this case would be 29 milliwatts. The amount of radiogenic heat production from basement is important because that quantity decreases slowly through time, as shown on this slide. Each isotope of the main radiogenic elements has its own half-life, all of which are very long. The fastest decrease in RHP with time is for potassium, followed by uranium, with thorium having the longest half-life. For relatively young Cenozoic or Mesozoic models, the decrease in RHP may be too small to worry about. But for Paleozoic or older rocks, it can represent a few percent of the total. As this plot shows, RHP from potassium today is about 23% less than it was 500 million years ago. The smaller decrease for uranium and the very minor decrease for thorium give us an average reduction in RHP for a typical granite of 6.4% from 300 MA to present day. Consequently, if our basement heat flow today is 58 milliwatts, with a maximum of 60% of that heat coming from radiogenic decay in the crust, the basement heat flow 300 million years ago, when maximum paleo temperature would have been reached, could actually have been 60.4 milliwatts per square meter. The difference is not large, but let's see if it significantly affects the calculated RO values. This slide shows the comparison between measured and calculated RO when we consider the maximum likely effect of radioactive decay on basal heat flow through time. The inset shows the decreasing basal heat flow through time. We can toggle back and forth a few times between the two models, that is, with and without the decrease in heat flow through time, to see that there is a small increase in calculated RO values when the paleo heat flow is higher. However, although the change is in the right direction, it isn't large enough to change the slope of the calculated RO curve enough to give a fully acceptable fit to the measured RO data. So we apparently are going to need another heat source in order for our calculated RO line to have the same slope as the trend of measured RO data. So we've made good progress toward the goal of simultaneously fitting thermal data from today, temperatures, and from the past, RO. But we have simultaneously uncovered a significant issue. The present-day heat flow of 58 milliwatts fits the present-day temperature data, while a higher heat flow at about 300 million years is required to fit the reflectance data. So what is the actual shape of the heat flow curve through time? What is our next step in putting the heat flow story together? Well, I'd pause here and ask a question about data quality before I dive into modifying the model. I'm not concerned in this case about the measured reflectance values, although RO quality is in fact often a problem. I've already said these RO data are almost certainly as good as reflectance values can ever be. Instead, my question is about the quality of the calculated RO values, which were obtained using the standard Lawrence Livermore National Laboratory Easy% RO equations. Easy% RO has been in common use since about 1990 and has been subjected to much scrutiny, but not to public testing. And the RO values in this well are quite high, where applications have been much less frequent than in the main oil window. Therefore, we should be cautious about demanding a perfect fit between measured and calculated RO values, since we cannot be completely confident that the calculated values are correct. So we'll now begin to change our thermal model to better fit the measured RO data. Just to refresh your memory, here's the model with a constant heat flow of 58 milliwatts and the original proposed Variscan erosion of 2,620 meters. Increasing the basal heat flow at and near 300 MA to 75 milliwatts per meter squared gives a calculated RO slope that is similar to that of the measured data. However, we see now that the calculated RO values are much higher than the measured ones in the Upper Carboniferous section. It is thus clear that in order to fit both the slope of the measured RO trend and the actual measured values, we will have to reduce the amount of Variscan erosion in our model. Doing so will reduce the gap in calculated reflectance across the Variscan unconformity. Decreasing the total amount of deposition and erosion at the Variscan unconformity from 2620 meters in the previous model by trial and error to 1950 meters gives us an excellent fit to the measured reflectance data, as shown here. The discrepancy between the dots and the calculated line at extremely high maturity is mainly a consequence of the limitations in the Easy% RO equations for calculating high reflectance values. It is of no significance for this discussion and shouldn't lessen our confidence in the excellent quality of this fit. To achieve this fit, I reduced the amount of deposition and erosion of each of 4 stratigraphic units, Westphalian B, C, D, and Stephanian, by about 25%. One of many alternative approaches would have been to omit deposition of the Stephanian completely and simply begin uplift and erosion earlier. The choice of how to partition a change in amounts of deposition and erosion should always be made on geologic grounds. The northernmost fission tract data points of Karg et al. That are closest to the M1 well actually showed half a kilometer less erosion than in our final M1 model. I think this is good evidence that M1 and Karg's nearby H well are close to the northernmost toes of the Variscan thrusts, where thrust sheets were thinner and where there was even very local marine Permian Zechstein deposition in some of the erosional valleys between the thrust sheets. After achieving the fit to the RO data, I rechecked the fit to the present-day temperature data. Fortunately, that fit had not changed noticeably, and thus I was able to use the same present-day heat flow of 58 milliwatts in this new model. Changing the maximum depth of burial will sometimes significantly affect compaction, which in turn affects thermal conductivity and thus the heat flow required to achieve a target temperature. Decreasing the amount of deposition and erosion at the Variscan unconformity only results in modest adjustments, less than 700 meters in maximum burial depth. There was no need to change paleo elevation, although it would have been acceptable to do so. These relatively modest changes do not invalidate the overall geologic concepts built into our model. The biggest conceptual change would be if we had decided to change the Stephanian from a period of deposition to one of erosion. Toggling back and forth between the original model and the revised model shows the minor differences in depths and in the tectonic subsidence curve. So the next important question is the source for the high heat flow of 75 milliwatts around 300 MA. This value is nearly 15 milliwatts above the value that would have been expected, even including the variation in basement radiogenic heat production through time. We cannot attribute the increase in heat flow to thinning of the lithosphere, since this was a period of compression during the assembly of Pangaea. I can think of 3 candidates. Perhaps you can think of more. One would be hydrothermal effects related to faulting and fracturing that is known to have occurred. The second would be volcanism, related more to local or regional zones of transtension or even rifting than to compression. The third would be emplacement of plutons. It is important to distinguish among these possibilities because they will have different intensities, durations, areal extents, and geological implications. This map shows latest Carboniferous to early Permian volcanism in northern Germany and southern Scandinavia, with the M1 well location indicated by the green star. Although there was no volcanism at that location, the copious volcanics, some hundreds of meters or even kilometers thick, to the north and northeast, suggest a good possibility of heating at M1 within the period from about 300 MA to 260 MA. Here we see our final model for paleo heat flow in the M1 well. It is derived from the concept of minor heating from the abundant volcanism to the north and northeast, and is highly empirical, though grounded in solid concepts. The baseline curve reflects the small decline in basement RHP with time. The high plateau represents rapid heating at the start of the documented volcanism in the late Carboniferous, followed by about 40 million years with relatively constant heat flow, and termination by rapid cooling at the end of the volcanic episode in the late Permian. All details of this reconstruction are negotiable if better concepts or additional age dating can be found. Other similar conceptual and numerical models could be created if one wanted to invoke alternative or additional mechanisms, such as hydrothermal activity. And here we see the result. The heat flow history just proposed yields an excellent fit between measured and calculated RO values. To summarize, in this discussion we have researched and reinterpreted an existing model and have then created a very different new model. The combination of significant gaps in the rock record and the tectonic complexity of the area have been responsible for most of the uncertainty in both reconstructions. This example is certainly not typical. It is far more challenging than an average reconstruction. But this exercise has sought to show the value of a fresh approach, fresh eyes, if you will, in evaluating a data set. It has also shown that even with good temperature and thermal indicator data for calibration, important uncertainties can remain. Those uncertainties represent, here and elsewhere, opportunities for good scientists to seize an advantage over competitors. Here we see a standard geohistory plot of the original model, with its high Variscan mountains, major Variscan erosion, rapid collapse into the sea to permit deposition of a thick Permo-Jurassic section, and the complete removal shortly after its deposition of that same lower Mesozoic section. The model fits the geologic and calibration data available, but is it even approximately correct? Here, in contrast, on the same time and depth scales, is the geohistory plot for the new model, with modest Variscan hills, absence of Permo-Jurassic deposition and erosion, and a slow relaxation of the Variscan landscape into the sea, ending in the Aptian. If we toggle between the two plots a few times, we can easily see huge differences. The new model also fits all available hard data. Is it better than the first model? I think so, but you will have to draw your own conclusions based on additional data, if you can find any, and on your own interpretation of the missing parts of the story. Finally, here is an annotated geohistory plot of the new model, using present-day sea level as the datum, rather than the standard Paleo sea level. Also shown are the tectonic subsidence curve and the final set of tectonic reference events I decided to put on the display. Not shown, because it unfortunately overlaps in time with the Variscan uplift event, is the proposed volcanic thermal event from the latest Carboniferous through the Permian. Before we conclude, I have one final surprise for you. When I finished this analysis, I decided to see how Nikolai Lopatin had handled the post-Variscan unconformity in 1971. I hadn't looked at his paper for decades and had forgotten most of the details of his model. Of course, he never discussed the elevation of the Variscan mountains because the burial history plot he invented didn't include water depth or elevation. But we can see here that he proposed that the maximum burial depth was reached at 288 MA, as shown by the red arrow. That's a little younger than my estimate. We also note that the trajectory of the rock layers is overall upward, meaning that the net erosion was occurring during the period from 288 MA to 100 MA, as shown by the green arrow. His sequence of events has periods of deposition alternating with slightly stronger periods of erosion. One wonders whether Lopatin envisioned his early Mesozoic depositional events as marine, continental, or a mixture of both. Lopatin's depositional scenario falls between that offered by my original model, with continuous marine deposition from 260 MA to 160 MA, and my final one, with continuous erosion from 300 MA to 114 MA. He proposed that about 2,000 meters of Carboniferous section was removed during the Variscan unconformity, very similar to the 1,950 meters I used in my final model, but less than my original estimate. However, his model has more total erosion at that unconformity because he removes Permo-Jurassic as well as Carboniferous. Finally, like me, Lopatin proposed a higher geothermal gradient at maximum burial than the one in place today. This difference is illustrated by the two temperatures circled in blue. The Carboniferous temperature was 190 degrees C, while the modern temperature at the same depth is about 170 C. Overall, his model has stood the test of time remarkably well. There are, of course, a number of aspects of 1D modeling that we haven't discussed here. We haven't mentioned lithologies or rock properties, such as compaction or thermal conductivity. We haven't discussed porosity optimization. We also didn't say much about water depths, lithophases, depositional environments, or eustatic sea level changes. In some cases, those points are key, but they weren't of great importance in this particular investigation of the M1 well. We also didn't say much about water depths, lithophases, depositional environments, or eustatic sea level changes. In some cases, those points are key, but they weren't of great importance in this particular investigation of the M1 well. Finally, we didn't mention source rocks, hydrocarbon generation, expulsion, or cracking at all. Perhaps we'll get a chance in a future video to examine some of those topics. Thanks for watching. I wish you fun and success in your modeling efforts.